Determine whether the function below is continuous at x equals 3. Use the definition of continuity to explain your answer. So the definition of continuity states, and I'm going to write this in pink. You don't have to actually explicitly state the definition, but if you know the rules, it might not be a good idea, might not be a bad idea to write them down. So we have a couple of criteria that this function would have to pass in order to claim it's continuous. So the first would have to be that f of 3 is defined. We would then need to figure out if the limit of as x approaches 3 of f of x exists. And then the third thing is that the limit as x approaches 3 of f of x must equal the value that we got of f of 3. So this is what we need to check. So you can sort of do these in any order as long as this is always last. You cannot claim this unless you're disproving continuity, but remember, the value of a function can be completely independent than the value of a limit. So you need to do these two things separately, then compare your answers, and then either claim it's continuous or not continuous. Also keep in mind, if any one of these fail, then the function's not continuous and you can stop. So as soon as you find a failure point, you can move on. But in order to prove that it is continuous, it has to satisfy all three things. So the first thing I'm going to do is I'm going to check, does f of 3 exist? So f of 3, this is a piecewise function. So if we go over here, 3 is included here. That means to calculate f of 3, I have to plug it into this piece of the function. So f of 3 is 4 times 3 minus 6. That's 12 minus 6, which is 6. So it passes the first checkpoint. The next thing we need to do is we need to check, well, does the limit exist? So because this is a piecewise function and we're checking it around value 3, there's a different equation for the left of 3 and a different equation for the right of 3. So these are actually going to be one-sided limits that we have to compare before we can check and see if the two-sided limit exists. So I'm going to check the limit as x approaches 3 from the left, and that means the equation I plug into my limit is this equation. Well, this is the very same equation I just plugged f of 3 in, and this limit could be done with direct substitution, so we can see that we're going to get 6. So please, please, please do not be the student that looks at the one-sided limit, sees that these two match, and then tries to claim this, because that's not true. This is a two-sided limit. You're not done with the limit step until you've looked at both sides. So now we have to see what the limit as x approaches 3 from the right looks like. So this is the equation that I have to use for my limit. If I try to evaluate this limit, I'm going to get 0 over 0. It may be tempting to do L'Hopital on this limit, and technically speaking you could, but these derivatives could get ugly and gross because we have all these radicals in play. So it can be done using L'Hopital, but it may not be as nice and clean as just simply using the conjugate. So the conjugate allows me to eliminate two radicals at the same time. So I'm going to multiply the numerator by the square root of x plus the square root of 3. That means I also have to multiply the denominator by the same thing. So now my new limit is the limit as x approaches 3 from the right of x minus 3 over x minus 3 times square root of x plus square root of 3. These x minus 3's cancel. So I get the limit as x approaches 3 from the right of 1 over square root of x plus square root of 3. So remember, with limits, we try direct substitution, it didn't work. Then you try an algebra move, clean up the problem, then try direct substitution again. If direct substitution still doesn't work, look for another algebra move. So direct substitution would mean plugging 3 in. So I would get 1 over the square root of 3 plus the square root of 3. That's perfectly fine. So this limit is 1 over 2 root 3. Well, 1 over 2 root 3 is not equal to 6. So the limit as x approaches 3 of f of x does not exist. So it actually fails the second checkpoint. So we can now claim f of x is not continuous at x equals 3. Now, suppose I had done these limits in the opposite order. Suppose I had done this step first, and I actually did the right-sided limit before I did the left-sided limit. So alternatively, what would have happened was step 1 would have said f of 3 equals 6, so it's defined. Step 2 would have yielded that the limit as x approaches 3 from the right of f of x is 1 over 2 root 3. I actually already have enough information to claim the limit is not or the function is not continuous there, because no matter what the left-sided limit equals, the best case scenario, if it exists, is that it's also this value. And these two values do not agree. So if you had done the steps in this order, you could have said, well, 6 is not equal to 1 over 2 root 3. So the limit as x approaches 3 of f of x does not equal f of 3. So the function is not continuous at x equals 3. So there's a couple different paths, because really depending on the order you see the steps, you might find the failure point, if it exists, at a different spot. But just make sure when you're reviewing continuity problems that you remember the way to show something is continuous versus the way to show something is not continuous. As soon as something fails, it's over. Shut the problem down and you can claim it's not continuous. But in order to show that it is, it has to satisfy all of the criteria.